Good. So the first part is just on linear magnonics. And I know I have a missed problem here. What is this? Okay. Now it should work. It says my computer has a too high. Okay, let's get started. Okay, you heard a lot about dynamics, especially this morning in the talk of Pietro already, including all the spin orbit talks. I'm not going to talk about spin orbit talks in my talk. I talk about magnonics. And you have to understand magnonics the same way like you understand photonics. It's just the science of not photons, but magnons. And then the first question arises, what is a magnon? And I would just like to show you this very simple animation here, what it is. Just assume you have an ideal ferromagnetically ordered one-dimensional system. So then all the moments would be aligned in parallel to each other. And of course, the ground state is always a boring physical object. More exciting is an excited state. And what is the first excited state of the system? Well, the answer is very trivial. You just take out one of the moments here, one spin, let's say, and you just take it out. And then you would just, hey, what is this going on? And then you would just put it on in the reverse direction. What you all notice is that the magnetization is reduced by 2 units. But you also notice this costs you a lot of energy here, exchange energy, because you have to break the exchange energy here and there. And then you have to pay it again when you put the spin here into the system back in the reverse direction. So that is expensive. But if you ask quantum mechanics tells you that the first excited state, hey, what is this? That the first excited state is a reduction in the saturation magnetization by 2 units, 2 times mu Bohr. But you can get it somewhat cheaper because this is a requirement. But what can happen is that I'm fighting here with the system. So what is going on here? But you can arrange a system where you have the reduction by 2 units also by counting each moment here a little bit. And if you really carry it through the calculation, what you find is this is not yet the ground state, but the ground state is just a superposition of waves. And what you end up here is just a wave, and the quantum of the wave is a magnon. So this is exactly 1 magnon, which reduces the saturation magnetization by 2 units. We can understand it classically very easily, simply just assuming that we have a magnetization in an external field, and then we can pull out the magnetization. You know what classically happens. A torque is formed. We have seen it this morning in Pietro's torque, and this torque results in the precession about the direction of the external field. So that is very, very clear. But we also have, if you have many of these moments, all exchange coupled to the neighbors, plus perhaps a little bit of dipolar coupling, because this is a collective excitation, they can all precess in phase, like you see here. That is ferromagnetic resonance, or there could be a phase difference. So you can have phase fronts, which you see very nicely here, the horizontal phase fronts. And if you look with another angle of observation, you can very nicely see how a wave is now propagating here. I think if you have seen that, you understand what a spin wave is. And so we have the spin waves and we have the magnons. To do it a little bit more detailed, one thing is missing here. Hey, what is this here? Yes. Oh, I think to move on. So what I would like to cover here is just a little bit about the basics of the spin waves, which we already started with. I will talk about magnonic waveguides. And then the particular property of magnons is these are waves, and waves can interfere. And then we can, of course, always think about what kind of applications can we create with interfering waves. You know that photonics is very successful. You wouldn't sit in front of your high-speed connection if there wouldn't be photonics, which means just fibers, fiber connection to your computer. And of course, if you think about waves in small magnetic objects, you can think about computing using magnons. I'm not going very much in it. I'm mostly talking about the fundamental aspects of that and what are the fundamental equations behind, but we always keep an eye where potential applications are. And what I will talk here in the first lecture is just Magnum interference. There's a very pronounced Magnum Caustic effect, which I find personally very interesting. And we even can realize some very specific atom physics mechanisms, the Magnum stirrup device, and if I have time, I will just go through that one. So fundamentals. We have seen this one here as a processing moment. So if you apply an alternating field from a microwave source with the right frequency, you can excite the magnetization here to precession. We have already seen if this precession is in a magnetically ordered medium, ferromagnetically ordered medium, waves can be created. You see how the waves are propagating here from the lower left to the upper right corner. What we can do is we can identify the wavelengths. We can also identify a wave vector. That is a picture you have seen before. So the cross product of the magnetization or the magnetic moment and the effective field is a torque which acts perpendicular, always a cross product, right-hand rule. And if you write it down, you end up with the Landau-Lifshitz equation. The property which enters the Landau-Lifshitz equation is here, especially the dynamic magnetization, which I always indicate with small letters, like you see here in the starting ones are the large letters. The Landau-Lifshitz equation has this torque term, but there's also a damping term because nothing lives forever and the magnons have a finite lifetime. And that is a very phenomenological term, a kind of viscous damping because it's proportional to the time derivative of the magnetization. And again, you'll find here a cross product. And if you work it all out, you'll find that the damping actually provides a force here on the magnetization towards the equilibrium direction, which is along the effective field. So damping is important and the torque equation is important. So we have seen that. And so this wave has a wavelength, and of course 2 pi over the wavelength is a wave vector, so we have a wave vector, and we now can discuss dispersion properties like you can do for any object, like you do it for photons, or you do it also for electrons in a solid. The photon dispersion is always very boring because it's a linear dispersion, as you know, and the slope of the dispersion is just the speed of light. So nothing very interesting, but you will see in a second that this is much more exciting in the field of spin waves. Why is that? First of all, spin wave physics or Magnum physics or magnonics, depends how you would like to call it, has two interactions acting. One is the exchange interaction, which is always generated if you have neighboring spins or moments which are twisted against each other. That causes exchange energy. And then you have the dipolar energy because you have magnetic poles, and magnetic poles have a long range interaction, dipole-dipole interaction, like you learn it in the second class when you study electromagnetic properties. So this dipole-dipole interaction is very important here. You know best dipole-dipole interaction if you grab two magnets on your refrigerator in your kitchen, and then you can really virtually feel how these two magnets interacts, and you also notice that it's dipole-dipole and not monopole-monopole interaction. Today, I will mostly discuss one specific material that is different from that what you heard in the first lecture. That is just yttrium iron garnet. And we do that for the very simple reason that it's a material with the lowest Magnum damping of any known material, any known practical material, actually, I should say. A very complicated material. You see the unit cell here, but you can grow it with very good level of purity. You can make single crystals and you can make wafers. Here you see a single crystal 3-inch wafer. So that can be produced, and that can, of course, be patterned into small structures and so on and so on. So that is very, very, very useful. Okay. If we put everything into account, we consider exchange interaction, we consider dipole-dipole interaction, then we get the dispersion. Here you see the limiting case that only dipole-dipole interaction is acting. And then you see it depends on the relative orientation of three quantities. Number one is the orientation of the film. Here you see the film, just a square. The direction of the external field and the direction of the wave vector. Yeah, you have three quantities. And if the propagation is in the film plane, then we have to distinguish between this mode, propagation perpendicular to the field, we call it the surface mode, or in the other case, if propagation is along the field, we call it the backward volume mode, that is this red dispersion curve. And if the field is perpendicular on the film, we find the forward volume mode. Just the names, you will see in a second why this is called a surface mode. This is called a backward volume mode for the very simple reason. Look at the dispersion. So with increasing wave vector, the frequency decreases. And so the group velocity, but it's always a slope, the group velocity is negative. So if the magnetization points in one direction, then the propagation is if the wave vector points in one direction, then the propagation is actually in the opposite direction. So group velocity and phase velocity are opposite to each other. And therefore it's called a backward volume mode because it runs backward. Okay. So actually, just to illustrate this a little bit, you might wonder, why is the dispersion of this green mode, the so-called surface mode, and the red mode here so opposite to each other? Well, the answer lies, like so often, just in the magnetostatics. Yeah, just consider how such a mode propagates. And for that, I show you just this picture for the surface mode. What you have here is simply, if this is a wave vector of the propagation, then you have seen then the magnetization is perpendicular, so the moments lie in this direction, they precess. But just take here this particular graph, and you can just plot the dynamic magnetization, the dynamic part. Just shown here by this blue arrow, like little magnets, and you see here is a particular case where these magnets are oriented head to head. And you know, if you have two magnets, this is a very strong force which tries to pull the magnets away from each other. Yeah, so it's very strong, and of course this costs a lot of energy, and therefore you have to work at a higher frequency to get this mode excited. But if you do the same for the backward volume mode, now you see the moments are oriented along the wave vector. And now if you do the same thing, if you just grab the dynamic magnetization, here's this blue arrow, and here's a blue arrow, you see now you have two magnets which are oriented anti-parallel to each other. And you now have a very strong attractive force. And attractive force means lower energy, and therefore the frequency here is lower. So by these arguments, just think in terms of little magnets, you can easily understand why the dispersion is so different. And this gives us, of course, a lot of freedom in designing magnonic properties. If you would like to build a device, you can choose any dispersion in between these two limiting cases just by changing the propagation direction. And you will see some nice applications a little bit later. So this works very, very well. If we have a film, actually, here you see a film of finite thickness, then you can also obtain thickness modes. These are modes which propagate forth and back between the back side of the film and the front side of the film. You can also have surface modes. You have just seen the green mode in the blue graph before, which only have a precession amplitude. There's a precession amplitude, what you see here on one side or on the back side. So all these modes do exist. And if you put everything together, so the standing modes, the backward volume modes, the surface modes here, or the forward volume modes, and exchange interaction, then that is the final dispersion properties. So very complicated, but I think you now have a good guide through that. So you see that now with increasing wave number, actually all the frequencies increase. That is just increasing amount of exchange energy, because if you go to larger wave vectors, then of course the twisting between neighbored moments becomes increasingly strong, and correspondingly the energy contribution from the exchange interaction. Okay. Let's do something useful with it, and that is simply, let's just propagate such a spin wave along a Higgs stripe, and you can consider the Higgs stripe here as a waveguide. The same thing like a fiber in fiber optics. And you have a substrate. The substrate is gadolinium, gallium, garnet, a non-magnetic material, only serving as a substrate. And what you can do is you can simply put a little wire across such a waveguide, and then you can connect the wire to a microwave generator. So you have a microwave current, and if you have a current through the wire, you know what happens. You generate Ørsted fields. If this is a microwave current, the Ørsted fields are oscillating, and of course this oscillating magnetic field excuse me, makes a torque on the magnetic moments in the Higgs film, and in this way you can generate a spin wave. And I can just show you how it works. Just excuse me, this is a picture of an experimental realization You see here in black the Higgs stripe, just a small section of the Higgs stripe, and a field is applied, and then you can see here this antenna in the middle. There are also two other antennas which don't matter here. And if we now put a microwave current here through this antenna structure, we generate spin waves which propagate away to the left and to the right. And we do it for the backward volume mode. And this is actually done here with Brillouin light scattering. I explain a little bit later what that is, but just see the data. You see now in the simulation, in this measurement, how modes are formed, and you see how the modes propagate away to the left and to the right side here in a symmetric manner. So this works very, very well. We can do the same for other geometries. For instance, we can do it now for the magnetostatic surface mode. So for this mode, where I said already, it's localized on a surface. And let's just see how this looks like. And surprisingly, these modes now only propagates to one side. So the symmetry is broken. So this is a very dedicated mode, which is nowadays often discussed in the framework of topological effects, because of course this is a topological mode. So that happens here very nicely. This mode is actually located to a surface that is a side view of our stripe, of our waveguide structure. And you see that the precession amplitude for the modes propagating to the right is located on the front surface, and the precession amplitude of the mode propagating to the left is located on the back surface. And if you would like to understand it better, just look at this animation. Here we have a mode now which propagates here from the left to the right, and then you can very nicely see how the mode is propagating, and you see the precession amplitude is here at the top side, from the right to the left, please excuse me. Yeah, and how can you change the propagation direction? Very simply, you simply have to invert the direction of magnetization. You see these moments here now point into the opposite direction, and now you see that now really the modes propagated from the left to the right. So we have this unidirectional property in magnonics, very important. So, okay, let's see what we can do. Waveguides. Waveguide physics is actually a tick more complicated, but this again gives you additional degrees of freedom in designing things, because you have finite bits here of the waveguide. This is a waveguide running from the front to the back, again an antenna for excitation. And what you see here already is a picture which we have measured with Brillouin light scattering. So that is an intensity picture. We measure it as a local intensity distribution this way. And what happens is simply that we have different modes which can be pinned here at the boundaries, because we have to fulfill boundary conditions on the side of the waveguide. And let me just tell you what I mean. If it is pinned, we have a mode with no node inside the film. So that is this one here. We have a mode with one node across here, the film width, or two modes, and we might have even more. And these modes have slightly different group velocities, like you see here. So these modes, if they all are excited, are beating against each other. They are creating interference patterns, and you have already seen such an interference pattern here in this stripe. And what we have to do mathematically is rather trivial. We just describe the modes with cosine functions and corresponding amplitudes. We have the superposition of these waves. We have to take the square of the sum in order to get the intensity distribution. And if we calculate it for this case, and if we take only mode 1 and 3, we get this picture. It looks like a chain which holds here actually. And if we only take mode number 1 and mode number 2, we get this snake-like picture, what you see here. And we can compare it to the experiment. So that is an experimental data, and you can see here the chain-like properties, because you see the hole here in the middle. Just compare here to this picture. So that works very well. We can even make some tricks experimentally. The good thing, if you do experiments, you have so many degrees of freedom which you can vary. For instance, you can build in a screw, like you see here. So these are 1 micrometer wide modes. And then you see mode conversion. And after the wave passes through the screw region, then you see here a superposition, which looks like the superposition from the n = 1 to the n = 2 modes. So this all exists. Here you see again a comparison, and I find it rather convincing that you can identify here this mode superposition. Of course, you can do a full-blown program just analyzing the intensity, fitting the amplitudes of the different modes. Also, the phases are very important. I did not discuss the phase here. And then you get it. You get even small details like an edge mode, a mode which is just located here to this discontinuity here. So this happens all. And if you would like now to see the full-blown picture, then you write down the Landau-Lifshitz equation like you see here. Let's get always here this picture. Maybe I can move it out here so that. Okay, then you get the full-blown Landau-Lifshitz equation. You have this term here. You have the damping, which is not shown here. And essentially, you have an acting effective field, and this effective field is an external field. It's a dipole-dipole interaction here written in a Green's formulation, and you have the exchange term. And if you do that for a film of finite thickness, 6 micrometer in this example, you get all these modes, and you can identify now what you have learned before. That is done for a somewhat larger wave vector range, and it is also plotted for positive and negative wave vectors. Then you see the surface mode here again. You see the backward volume mode. You see the increase due to exchange interaction here on all at high wave vectors. But you can see something more. You get all the standing wave modes which propagate between the front and the back of the surface. And if you like to take another angle of view on this kind of data, you can consider this here as a long continuous range of frequencies, because the frequency spacing becomes very, very small here, where you can excite magnons in such a system. And you find something else which is also very exciting. You see there is a minimum here at a finite wave vector. And this leads us to the second part of my lecture a little bit later, where I will talk about Bose-Einstein condensation. So this all is there, and so let's move on. And yeah, just the experimental part. It's Brillouin light scattering, and that is actually nothing else than, if you like to discuss it in the particle picture, scattering of photons from magnons. The most easiest way is to do it in second quantization. It sounds complicated, but it's fairly easy because you have particles, incoming photon. A photon can be scattered by either generating or annihilating a Magnon quantum, and this all happens under conservation of energy and momentum. Energy means frequency, h bar omega of f here. And so if the photon just creates a Magnon, the frequency is reduced because you have to generate a Magnon of the corresponding frequency. And if a Magnon is annihilated, then the frequency is increased. And it shows up in the experiment as side bands to incoming laser light. So that is a laser light. Then you see the side bands, and the frequency shift is just the frequency of the Magnons, of the spin waves. And this is done with Brillouin light scattering, an optical technique with Fabry-Perot's, and it works very, very conveniently. So we use a Fabry-Perot interferometer, where we take advantage of the fact that light only passes such an element if the spacing is a multiple integer of half the wavelength. Actually, it's a little bit more complicated because we do multipassing Fabry-Perot interferometry, but that is not so important here. So we need a laser, which shines a laser light on the sample. But what you see here is a couple of other things which we can use. First of all, we can focus onto the sample, so we have a local means. So we can scan across the sample and get a two-dimensional picture, like you have seen before. We can also excite the spin waves with pulsed microwaves, and then we can measure the time between launching of such a generation pulse and the detection of the photons from the inelastic light scattering, and then we get temporal information. So we can make little movies, and you have seen such movies before when I showed you the initial videos of the propagating backward volume mode and the surface mode. We can even do more. We can change the angle of incidence, and then we get wave vector information, because conserved in the scattering process is just the in-plane component of the wave vector. And we get pictures like this. Here you see the Brillouin light scattering frequency measured as a function of the wave number. Wave number translates into the angle of light incidence here on the sample. And we get here very nicely the backward volume mode. Here there is a 6 micrometer thick thick film. We also get signals from the phonons, and we see it at positive, so the Stokes signal, and we see it for negative frequencies, so the anti-Stokes. So that works very well. So let me just demonstrate an example where we use Magnum interference now. That was actually the very first logic element we have built based on spin waves. And the idea was very simple. The idea is just to have two waveguides. We excite spin waves in both waveguides, brings them to interference via this detection antenna, so it's electronic interference, if you like. And now what we can do, we can just shift the phase of a propagating spin wave by putting a little wire across the sample. Just think about what happens if you have such a wire. The wire carries an electric current. The electric current generates a local field. And now you have to imagine what happens with precessing moments in a local field. If the local field adds to the bias field, then the local field is, then the total field is somewhat higher, precession is faster. And if the local field subtracts to the bias field, then the internal field is smaller and precession is slower. And this translates into a phase shift, which is positive or negative. And indeed, if we plot the phase shift, this is now measured data, as a function of the current through such a wire, you see we can achieve a phase shift of pi or 2 pi easily within the available parameter range. So what we can do, we can put either a current through this waveguide or through this waveguide and measure the interference. And that is the measured signal of the interference. And 0 means no current and 1 means current. And then you see, if you go through this and if you compare to the truth table, what we have here is an XNOR gate. So we can easily build an XNOR gate, and with that we can span the entire family of logic gates if you would like just to mimic CMOS logic. So that can be done. Let me show you one experiment which I like very much. We replace this geometry with this fork-like geometry. So that is a magnetic film. Yeah, it has a fork-like structure. So two branches where we actually generate spin waves here. And then we let them all interfere here in this region. And we can actually measure them electrically here. And again, we put a wire here across to locally change the phase of the propagating spin waves here. And again, we use Brillouin light scattering, and let's do the experiment. So if we launch now spin wave pulses and let them propagate, here they are unified, and you see they interfere constructively because the maximum of the density is here in the middle. And now let's repeat this experiment, and now let's put a DC current through the wire. So we shift the phase, and the current was chosen that we shift the phase by pi. Then you see now that now in this case, again, you cannot see nothing because you only observe the intensity. But if now these two pulses interfere, you see we get dark region between these two pulses. So we get destructive interference here where the two peaks here would like to overlap. So if we translate it into the output, we get a minimum if we have destructive interference, and we get a maximum for constructive interference. So we have a nice logic element, not very useful because here we use Brillouin light scattering, or in this case here a wire, to detect the output signal. So device which is much more suitable for interference-based logic is a majority gate. And the majority gate has a very general idea that we use waves with phases. So the information is coded in the phase of 0 or pi, corresponding to logically 0 and 1. And the output is always the majority of the input signals. So if the majority is zeros, then the output is a 0. If the majority is pi's, then the output is pi regarding the phase. And such a thing can be very easily built just by having 3 waveguides, which are then combined, and then we can measure the output phase. And that is a lot of data which Tobias Fischer in my group has measured. And what he finds here for the output signal, this is all experimental data, is exactly the functionality of a logic gate. I will not go through the details. Let me just show you some more data. This is now numerical simulation because students love to do numerical simulations. The point is how effectively does it work? And with numerical simulations, you can realize some details which are much harder to get experimentally. For instance, if you build this kind of device, you see a lot of waveguide modes here, many modes, and then you should get a then you should get a good interference pattern. You also get parasitic generation of modes which run out of this region because they are partly reflected here. So many things which are not well controlled. If you measure the output signal, it's only 11%. So, well, it's just okay. But if you now go to a different geometry, then you, for instance, if you go to a forward volume mode geometry, then you get already a better signal, you get 19%. And if you now would further like to increase it, the students came up, this was Stefan Klingler, just by making it a little bit asymmetric. That is good for suppression, so the reflections, and in this case, he gets 64% just by numerical optimization. So this works. And one can move on, one can study caustic effects. Caustic effects are very pronounced in magnonic systems. So what is caustic? You all know caustic, I mean, in the area where I live, here in Rhineland-Palatinate in Germany, caustic effects are very well known because you find them always if you have a glass of wine in front of you. If it is red wine, you have red caustics. And that is just if the sun shines through your glass, you see here spots of very high intensity. That is just caustics. You can control caustics, and I found this very nice YouTube video here where people have used this effect to modulate the thickness of a plate. And if you rotate the plate in the sun, you suddenly see a picture of Alan Turing here, just generated the same way like a pattern. You create the patterns here with a glass of wine. Another caustic effect, which is very well known, is of course a rainbow, because here we use specific reflection properties of a drop of rain. So you get this nice rainbow here, even with the different colors. Let me now show you what this means in terms of magnonics. We take a very special experimental setup. So we now use a large film with some kind of waveguide connected to it. So the total shape is like a panhandle, if you like. That is 6 micrometer thick. So what happens is here again is an antenna. So we generate spin waves here. They propagate along the waveguide, and then they enter here this larger region. And being an experimentalist, let's first do an experiment. And here it is. And what do you see? Something very exciting. The wave doesn't create just spherical waves here like you would think, like you would throw a stone into a pond of water where you could get the spherical rings. Instead, you get a very directed beam here. So that is unusual. And why is that? So let's just discuss it a little bit. What we need to discuss is the waves, and the waves have a wave vector, which is here, and they have a group velocity. And the phase velocity is along always the wave vector. The phase velocity is this direction, and the group velocity goes here into this direction. Of course, we have to ask ourselves, why is that? And there are many ways how to introduce this, and I mostly like to discuss it here along this line. Let's simply take the dispersion curves, which you have seen. And from the dispersion curves, we can calculate a so-called isofrequency curve. And that is all the data in the KZ, KY plane, and that is just this plane here. You see that is a Y direction, that is a Z direction. That is the same thing like here, but now in the reciprocal space. Yeah. And then let's calculate all the positions where we find in the dispersion curve a wave for a given field. And the field is shown here, 1840 Earth. That was the field in the experiment. And then we find that is a curve where all the data lie. Yeah? That is an isofrequency curve. So all x, kx, ky pairs fall onto this line. And this line is very important for us because if you would like to know the group velocity is always perpendicular on the isofrequency curve, because the group velocity is the omega over decay, just this quantity, yeah. And if omega is constant in our case here, because we choose a fixed frequency here, then decay is always perpendicular to this curve here, just by the mathematics behind. So these are the group velocities, and k is just shown here again for different values, and for all these values the group velocity is parallel. So we create many waves with different k vectors, but since the group velocity is always parallel, we get these two beams, these two caustic beams, like we name it, which go here into these directions. And that is exactly why we get this experimental results. Actually, you see something more. This wave is refracted from the boundary, and then it actually continues like this here. We can do another experiment, a different frequency, and then the isofrequency curve looks a little bit more rounded. Now we get here group velocities in all different kinds of directions for the corresponding wave vectors, and now we see radiation of spin waves here from the entrance from the waveguide into the free film area, which now goes here in all directions. So this works very well. If you take just the dispersion curve you have seen before, easily calculated, from that you can calculate the wave vectors and the group velocities by the simple derivative you have seen before. And then we get here experimental data like you have seen, and here we get just numerical results, and you see the very nice agreement between these two things. So many things can be done. It can also be done in permalloy, it can be done in cobalt iron boron and other materials. So this has been shown by many people. Okay, my time is running very, very quickly. Let me stop here at this point. I have actually I wanted to show you let's stop here and let's now go to the nonlinear part, if you agree. So this is now the nonlinear part. Can you see? Why is this? Sorry, I guess I have to adjust it again here. Bildschirm wasn't so einrichten. So what we discussed so far, it was all linear. The caustic is a linear effect. But of course, one big advantage of Magnons is they are intrinsically nonlinear. If you would like to know, just look back into the Landau-Lifshitz equation of motion. You have a cross product of the magnetization and the field, and both terms are time dependent. The magnetization truly, because we have a precessing magnetization, so it's that. But along with the magnetization comes, of course, also the dipolar fields, which are also have a component which is precessing. And therefore, we have a cross product of two time-dependent quantities. So we have a nonlinearity, quadratic nonlinearity intrinsically in the Landau-Lifshitz equation of motion. And that is very remarkable because this quadratic nonlinearity is intrinsic. Think about photonics. You know how important nonlinear photonics is. But for that, you always need a medium to provide the nonlinearity, because the dispersion in photonics is always a linear thing. What I would like to show you here is just a quick introduction. I will show you the Magnum Transistor, which helps us a lot in making logic elements. And then, of course, I have to talk about the Bose-Einstein condensate, because my ERC project, where we study these phenomena, was already mentioned by the chairman. So, introduction into nonlinear interactions of Magnons. This picture to the right, you have seen now. But what you now might simply do is think about it in terms of magnonics. And magnonics simply means that we have quanta of magnons. They have energy. And now my mouse is gone. Let's see. Okay. We have quanta of energy. The quantum of energy is very trivial. It's just h bar times omega. They have linear momentum. They have mass. The mass simply comes from the dispersion. You know that the mass is just the curvature, the 1 over proportional to 1 over the curvature in the dispersion, like you assign effective masses for electronic band structures, the same thing. And we have the nonlinearity, and this will lead to 2, 3, 4 Magnon scattering, and so on. And let me discuss this. But before we do that, let's just think a few words about the Magnum distribution, because we work at finite temperature. And so what we have to consider here is the Bose-Einstein distribution function. You know this function very, very well. You just have the number of states, d of as a function of frequency, d of omega. And then we have this exponential factor, which you know from the Bose-Einstein distribution function. And what matters here is just the energy, h bar omega, the temperature, and we have the characteristic -1, because that is Bose statistics and not Fermi statistics. What should, for completeness, also be added is a chemical potential here, which you know from electronic band structure maybe. What we can do, we can plot this function, which you see here. I do it in a very special way because I log the quasi-particle density, so the number of magnons, which classically is just the intensity of the magnons, as a function of the logarithm of the frequency. So there is a log-log plot. And what is very remarkable is you have seen in the dispersion, we get a minimum frequency at some finite wave vector. So that is a minimum frequency what we have. And then if you plot this function, it is just this blue curve. And that is for a finite temperature T, and we assume the chemical potential is 0. So that curve is very important. Just for curiosity, and I will come back to that a little bit later, what happens if now we have a finite chemical potential and with an eye of mathematics? The interesting case is, of course, what happens if h bar omega, so the energy of our magnons, becomes equal to the chemical potential. Yeah, then you see this difference here is 0. E to the power of 0 is unity. And then in the denominator, we have unity minus unity. So again, a 0. So we divide the number of states by 0, which means that the density, of course, diverges. And then we get this green curve. So this is a very particular case, just only mathematically discussed for today, where we have, which happens if the chemical potential becomes equal to the minimum frequency. And that is actually the condition for Bose-Einstein condensation, a divergence, and it simply means that physically, this simply means that all the magnons like to go into one single common state, which is called a Bose-Einstein condensate. I will come back to that. Let's a little bit go back to the nonlinear processes. The linear processes which happen in our sample, I should say, unfortunately, is if we have a dislocation in our system, an imperfection, whatever it is, a few missing atoms, another element, some scratches, then we have magnons with energy epsilon1 and linear momentum p1. They just come here, they can get scattered, and the outcoming magnon still has the same energy because there is no energy transfer, but there could be momentum transfer. So the magnon can scatter into another direction. That is well known, and that is why we have to keep our samples as clean as possible. And that is why we love yttrium iron garnet, because it's single crystalline with a very low defect density. Low defect density means that this process becomes not very pronounced and is suppressed. Nonlinear processes. Of course, the most simple effect you could think about is a 3 magnon scattering effect. And we can think about 2 of these effects because you can always think in terms of time, and the time arrow can be forward or backward. So what can happen is that one magnon, this green magnon, decays into 2 other magnons. Energy and momentum needs to be conserved. So the sum of the frequencies of these scattered magnons must be the frequency of the incoming magnon. And that is called a 3 magnon decay process. And the opposite, or if you like to run the time backwards, is a confluence process where 2 magnons unified to a new magnon. And now the energy epsilon 3 is the sum of the energies of the 2 incoming magnons, and the same for the wave vector. And you can continue. The next process is 4 magnon scattering. There are several of them, and here is the most pronounced one. Just 2 magnons come in, they scatter, and 2 magnons go out. The total energy needs to be conserved, and the total momentum needs to be conserved. And this process is actually a very interesting one, because you see its particle number conserving. And this might remind you what you learned in the first year of physics, where you were just discussing scattering processes of atoms and molecules in a gas. So this leads to the Kinetic Gas Equation. Because of the strong analogy to just a classic gas of gas molecules like in the atmosphere surrounding us, the process, what is happening here, is called the generation of the Magnonic gas, and I will come back to that. Just remember the word Magnonic gas, and you achieve a Magnonic gas if you have 4 Magnon scattering enabled. Again, Brillouin light scattering, I'm just repeating here what we have seen before. We have seen Brillouin light scattering microscopy, where we can focus onto the sample, we can scan across the sample. It's only another picture, but it's the same process you have seen before. And we have also seen that we have spin wave conduits or waveguides, and that we can put a wire across such a waveguide and then create spin waves. If you would like to do it very efficiently regarding the microwave part, we work with coplanar waveguides, if you have heard that word, but otherwise it's not important. It's just important that we can locally create strong fields via the microwave currents for the excitation. Okay, now we use a coplanar waveguide because technically that is a very efficient way, and we can excite spin waves of very high amplitude. And if we do so, then if we make a spectrum, we see here the excitation frequency, but we also see signals at twice the excitation frequency or even 3 times the excitation frequency. And when we plot now the BLS frequencies as a function of the microwave frequencies, then you see we get, so that is the exciting part. We get signatures at twice the frequency, 3 times the frequency, 4 times, 5 times, even somewhere here in between. And the question is, of course, what is going on here? And now you have to start to think in the terms you just have learned, and that is the 2 Magnon, the 3 Magnon scattering processes. The linear regime is very trivial. We now take a Brillouin light scattering spectrum. So that is a signal which we generate with a microwave generator. So in the Brillouin light scattering spectra, we get a large peak at exactly the microwave frequency and some noise to the left and to the right. So that is the data actually measured with a very, very high contrast here. And then we get essentially, if we change the microwave frequency, the BLS frequency changes 1 to 1. So you see, if we excite at 10.5 gigahertz, we get a large Brillouin light scattering signal at 10.5 gigahertz. So, but now if we excite in the nonlinear regime, then we get here these interesting sidebands, what you see here. Yeah? And that is called spin wave instability. And actually what happens here is nothing else than just 4 Magnon scattering in this case. So we just take 2 Magnons here, 2 blue Magnons, and they scatter into the 2 red Magnons, and you see that the sum of the frequencies of the red one gives exactly here the frequency of the 2 blue Magnons. So we need 2 blue Magnons, of course, for wave vector conservation. Yeah. So these kind of processes happen. Here you see it happens also for the higher orders somewhere here. Here it's the same thing here for the 2F signal because the nonlinearity is still strong enough so that happens. So you discover many, many little details here in this data. If you do an experiment, you also find some other things that is only for the very experts among you. Here you see some signal from the phonons. So this happens, and if we drive it very, very nonlinear, then we even can cover all the area in between with 4 Magnon scattering. Yeah, that is with higher power. So nonlinearity plays a very important role. And now I would like to show you how we can use that actually to build a Magnum transistor. You remember all electronics started with the tubes, but tubes were the vacuum tubes were not very handy. Yeah, you could get a big radio and with a couple of tubes inside, usually not more than 4 or 5 tubes. And it was not really stereo at the beginning, and it was very bulky, and the radio became very, very hot. And the breakthrough happened when the transistor was invented. And what I now would like to show you is that we can realize a Magnum transistor in a very efficient way using nonlinearity. We need two ingredients. One is nonlinearity, and we need something else, which is called a Magnonic Crystal. So I have to take you now on a detour where I discuss the Magnonic Crystal. A Magnonic Crystal is nothing else than just an artificial material. In our case, we take yttrium iron garnet, and it is made artificial by cutting little grooves into it in a periodic manner, like you see here. So we obtain something like an artificial new lattice parameter, which is nothing else than just the separation between the grooves, like you see here. Yeah? And now we let the wave propagate it. And you know this concept from other fields of physics, of the photonic crystals are known, also sonic crystals are known. But here we now operate with the spin waves, and the spin waves are in the gigahertz regime. What happens in this case? Very simple. If you have the grooves do nothing else than just scatter spin waves. That is just 2 Micron scattering, the terminology we had before. And if a wave comes in, like this one here, then there might be this wave might be scattered here at the first imperfection. The second partial wave might be scattered at the next one at a separation of the artificial lattice parameter, so it goes back like here. And the third one just does the same game here at the third cut into the sample. And now you notice what happens. We get constructive interference if this condition is met. That means that the separation here, the artificial lattice parameters, is just a multiple, I formulated with these words, a multiple of half the wave, integer multiple of half the wavelengths. I put the 2 to the other side. So the lattice parameter is an integer multiple of half the wavelengths. And that is just a condition for a Fabry-Perot if you are familiar with optics. And if that happens, then you see all the incoming Magnons are scattered, or in other words, the Magnonic crystals becomes intransparent. And if you look into the dispersion, here again, you see the backward volume mode very, very schematically shown, only like a straight line. There's just the initial part, and then if we go through the minimum and increase again here. And I show it also for the other side, for the negative wave vectors. And if we now have this Magnonic crystal, then a gap is opening. Same thing, like the gap opens for the electronic band structure if you have a periodic arrangement of atoms, what you always have. Yeah. So a gap is opening here now in the dispersion of the Magnons, and propagation is not allowed for frequencies here inside the gap. And if we measure now the transmission of spin waves between this excitation wire and then a receiving wire or receiving antenna here through such an artificial Magnonic crystal, then we get for the transmission as a function of the frequency this characteristic minima. Minimum always means no transmission, and this is a decibel scale here. And that is always at the position where the condition that a multiple integer, an integer multiple of half the wavelength meets here the artificial lattice parameter. And that led us to the development of the Magnum transistor. And this goes in particular back to Andrei Chumak, who has done this work in my group. And as one of the outcome, I mean, if you think in terms of career, then Andrei got famous with this Magnum transistor, and he's now a full professor at the University of Vienna, a position which he just recently obtained. And I think the Magnum transistor has largely contributed to his scientific reputation, because he was the first to publish this work in my group. So the idea is just, we do essentially the same like you do for a field effect transistor. If you have a field effect transistor, you have a source contact, you have a drain contact in a semiconducting material. And then with a gate voltage, you create a little channel, and you control the channel width by the gate voltage. So that the current which flows from the source to the drain depends on the gate voltage. And here we do something similar. That is why I use just the nomenclature of a field effect transistor, so source, drain, and the gate, and here you see the Magnum transistor. And you might now notice we have three contacts. We have one contact to generate the spin waves here at the source. We pick up the spin waves with the drain contact. That's just done by induction. And then we have the Magnonic crystal, and across the Magnonic crystal, that is now new, we put a gate electrode. And now the idea is just as follows. If you remember the transmission between the source and the drain, yeah, you saw this characteristic minima if the Magnonic crystal condition is met. And now what we do, we want to propagate from the source to the drain, so we use a frequency for that, which is here where the transmission is very high. But here in the gate regime, we inject magnons, just applying corresponding microwave signals, with a different frequency, just where the minimum is. And these magnons cannot propagate because of the Magnonic crystal condition. So what happens here, these magnons stick there, or in another sense, this Magnonic crystal acts like a cavity for these magnons. These magnons may not propagate because as soon as they start to propagate, they are back reflected via the condition you have seen before, and so they are constantly confined here to this region. And now the final point is that, of course, nonlinearity becomes important. But let me just show, because I showed you now how the layout is. So what you have to consider is the system we have, the system we have looks like this, just a photograph. So everything is very large. And I like to show a picture of the very first transistor from 1947, which was also very, very large. It has nothing to do with the microelectronics we nowadays have. So you have here the transistor contact, and the rest is just some wiring and some mounting. And here's the same thing. That is a X stripe. Here you see very nicely the Magnonic crystal, and you see the three electrodes I was mentioning. And these are just contacts to the microwave sources. So let's see what happens. Now the nonlinearity. First, let's assume we generate magnons. I show them just blue, and the magnons, if they have the right frequency, they just propagate across the Magnonic crystal area to the drain, and we see a large signal here. Now we just throw in a few of these red magnons, that was a problem. We throw in a few of these red magnons, which are just at the condition that they are constantly back reflected. Why is this not working? Let's see. So again, I can't get it working, but it is important for your understanding. So let's get it again. So, okay, now again, we have to see this to watch this part here again. So the magnons go through if nothing happens here in the gate because they have the right frequency. And now we increase the number of magnons which exist here now in this gate region. They cannot propagate, but now magnon scattering takes place. And you see some magnons are scattered, they are taken out, and therefore the output current is reduced. And if we now put in many, many more magnons here, which you see now, then you see that now all the incoming magnons are scattered and no magnon gets through. Or in other words, with a small amount of magnons here in the gate region, we have controlled the large current. And that is the same thing like the transistor. With a small current through the base in a conventional transistor, you control a large current from the emitter to the collector. So that is the idea behind. Here you see it again. If there are no gate magnons, everything goes through. If there are a few gate magnons, that is just already narrowing in the CMOS analog, the channel between the source and the drain because of the scattering here in our case. And if we now have many, many gate magnons, this corresponds to the field effect transistor where the channel is now closed. And we can measure that. That is now experimental data, and you see how nicely here the pulse amplitude at the drain is reduced with increasing gate magnon density, given here in unit of the microwave power we have applied. So this works. And if we define a threshold, which we have always to do, then we see that the number of gate magnons and it's 0.1 then the number of the source magnons, or in other words, this transistor has already an amplification gain of 10. So this is, of course, not very convincing, but for the very, very first transistor, Magnum transistor in the world, that is already a remarkable result. And of course, this now asks for further improvement, for miniaturization. And Andy Schumack in Vienna is working on these kind of things, trying to improve it. So let me spend my last minutes now on Bose-Einstein condensation. You have already seen how important nonlinearity is. You have seen that we can tailor the dispersion. And now let's put it all together to create something new, which is a Bose-Einstein condensate. And for that, I pick up what we discussed a little bit earlier today. This full dispersion curve. You have seen this view graph before. Just remember, this is just a repetition. Landau-Lifshitz equation, we have taken out here the damping for simplicity. Acting as an effective field. The effective field has an external component. It has a dipole-dipole interaction because of, this long-range dipole interaction. We have the exchange interaction. We might have anisotropy terms, but I neglect them for the moment. And if we plot this curve here for the different geometries, we get all this spaghetti of modes. Shown is it here for the wave vector parallel to the field, so the backward volume mode geometry, and for the wave vector perpendicular to the field for the surface mode geometry. And of course, you can have all wave vectors in between. This goes, of course, continuously. This transforms continuously from this distribution here into that distribution. In other words, we have many modes here in this regime. And what is very, very characteristic, we have a minimum frequency here. Minimum frequency, which is a little bit more than 4 gigahertz here in this particular example. And that is calculated for a 6 micrometer thick big film. So, okay. Now, we have to think again about nonlinearity. And because I need to explain to you how do we excite now modes. And let me explain to you here parametric oscillators and also parametric amplification. You know all parametric oscillators from your childhood, because I assume that most of you like to sit on a swing like this little child here. And the trick with the swing is that you constantly move your center of gravity here up and down just by bending back if you swing upwards, and bending forward if you swing backwards. And this basically translates in a movement of the center of mass, what you have here. Yeah? So if you just start to swing, if you go down here, then the center of mass is low, and here the center of mass is high. So essentially, the curve of the center of mass is this one here. It's not just here a circle. Very important. Yeah. So you can actually work through that, and then you see that this is important. And essentially what matters here is this, the frequency by which you move up the center of mass is twice the frequency by which you swing. Yeah? Because always in this part, you put the center of mass low, and in this part here, if you cross the minimum, here you put the center of mass up, and then if you swing in the opposite direction here in the first half, again you put the center of mass low, and then in the second half you put the center of mass up. So if you look at it, the center of mass oscillates with twice the frequency by which you are swinging here on the swing. Let's have a look at this animation. It explains it to you. So that is just a classical precession. Precession can be non-circular, it can be elliptic, like you see here. And if we have that, then again you see that now the Z component of the magnetization oscillates, and it oscillates with twice the precession frequency. And now we use parametric pumping by simply applying an RF field with exactly the same frequency by which this here was moving up and down. And by this way we can couple to it, and we can amplify the precession amplitude, like you have seen here before. So that is the idea behind parametric generation. It works remarkably well. And let me just show you how this could be done. Again, this is a dispersion picture you have seen here before. I write down the condition for parametric pumping. It's actually always the same thing. We have conservation of momentum and we have conservation of energy or frequency. And now what we do is, if this is the system, we take a microwave source with this particular frequency. And this frequency generates now Magnons parametrically here at half the pumping frequency. You see that. Yeah? But you also see that Magnons are always generated in pairs of two, like these two pink ones. So that the total wave vector is conserved. A photon doesn't have a wave vector on this scale here. Yeah? It's the wave vector is, of the microwave photon is negligibly small. But making this kind of pairs, it always guarantees that the wave vector conservation is maintained. So we generate Magnon pairs here. We can generate other Magnon pairs with other absolute values of the wave vectors, but obviously the same frequency. And so we populate this part of the spectrum here. Now what happens is we have the 4-Magnon scattering process, and that results in a thermalization. So the Magnons will collect here at the bottom. Why is that? That is simply, I like to take the analogon of a coffee cup. What you have is, if you have, oh, sorry, I don't have it here, sorry. If you take the coffee and let it sit on your table, after a while the coffee gets cold because the molecules scatter and some escape outside of the coffee cup, and the remaining molecules are just reduced in their velocity and therefore the kinetic energy, and therefore they cool down. So some Magnons escape to higher regions, other go down, and at the very end of this process, what happens is that this particular point here in the dispersion is filled with many Magnons. They form a Bose-Einstein condensate. And I have already told you the secret behind. The secret is simply the Bose-Einstein distribution function, and you have to consider the chemical potential. If the chemical potential becomes equal to the frequency, then the population diverges. We have discussed it initially for the second part here. So that is the secret here. So again, let's have a look at it experimentally. We remember, I just show only one half here. Here we should have Bose-Einstein condensation. What I can do, I can only take this part, and for graphical reasons, I can rotate it here by 90 degrees. Then this is a wave vector scale. And now we can do experiments. And you remember that in Brillouin light scattering, we can measure with wave vector resolution. And here is such a measurement. This is all Brillouin light scattering measurements. So we now measure for a given frequency with as a function of the wave vector, and we do it with time resolution. So at time point 0, we inject the Magnons, and then what we see is how the Magnon gas here is filled. So this area here is now filled with Magnons, and then after a while the Bose-Einstein condensate is formed. It takes some time because all these Magnons have to trickle down here. This is the energy or frequency scale. They have to trickle down here to the Bose-Einstein condensation point, and then the Bose-Einstein condensate is formed. So this works very well. If we actually pump with much larger power, it doesn't work anymore because now we pump so strongly that the 4-Magnon scattering does not allow anymore, that everything goes down because the scattering is too fast. So no condensate is formed here. Actually, what we can do, if we do this very, very hard pumping, we can calculate the effective temperature in the Magnon gas. The number is 30,000 Kelvin. Whether this makes sense or not is up to you. It's just a number. Taking a Rayleigh-Jeans criterion, if you like to sell it, then we discuss Magnons which are hotter than the surface of the sun. You might do so. It might help you to remember what is going on here. So that the Magnon gases can be very, very hot, but this is Magnonic heat. That is not real heat. So you do not burn your fingers if you are doing this kind of experiments. So let's move on. Okay. I told you already that the idea with the coffee cup works. So actually there's a nice theory which we did by discussing the process, which is called evaporative supercooling of the strongly overheated low energy area of the Magnum gas. So that is this area which you see in the experiment here. And then a Bose-Einstein condensate is formed. Yeah. There's actually a much nicer way how to do it, and that is to measure for a little bit longer. And then we switch off the pumping, and then we only have the Magnum gas remaining. And what happens is that the Magnum gas is then, after switching off the pumping, which is here, the Magnum gas condenses here into a Bose-Einstein condensate. And what you see here is a measurement on a logarithmic scale, and you can actually see here 1, 2, 3 orders of magnitude that then the condensate decays over 3 orders of magnitude. That is just the contrast we have here in the experiment. And this representation linearly, but since this is an exponential scale here, a logarithmic scale, it means we have an exponential decay. And what happens simply here is that these magnons convert to phonons because of the damping, the Landau-Lifshitz damping term, which we have, the Gilbert damping, which is very weak, but it is there. But you see, we can operate with these states here over just a microsecond typically. So that works very, very well. So that is a time where we can actually do something useful with it. Okay. There are many things we can do. First of all, you can consider such a condensate as a new state of matter, like people sell it. For instance, if you discuss Bose-Einstein condensates in ultra-cold quantum gases or in photonics, you find that also. But you can do more. You can remember your background on supercurrents where Cooper pairs are formed. And the question is simply, do we have also something like a magnonic supercurrent? And the answer is yes, we do. And the answer is very trivial. Why that is? Because what is new here is this Magnon BEC. These are Magnons, so they have wave functions. And you have a total coherent wave function, single wave functions for all the Magnons which exist in the Bose-Einstein condensate. If you think about conventional superconductivity, again, you have one wave function of the Cooper pairs, which is the same thing. The density is, of course, the square, here the absolute square. And the phase is also defined, it's just the argument of the wave function. So we have a BEC density and the BEC phase. And the supercurrent, very generally, is always obtained if the phase has a gradient. So here, yeah. And the supercurrent is actually nothing else than just the gradient of the phase. It's the number of particles you have available and the quantity which you transport. And the Magnons are characterized here with h bar, which is just the angular momentum which is transported here, and also the effective mass plays a role here. So Magnon BEC. Next question, of course, is how can we manipulate now the phase? And everything is easy in magnonics. That is always my key message I would like to convey, because we have so good control on the system. For instance, if we look at this dispersion curve and plot it as a function of temperature, we can do so because we know that the saturation magnetization is temperature dependent. So we can just change the temperature, and correspondingly we can change the saturation magnetization. And then you'll see that if we change the saturation magnetization between these two values, 170, 150 Gauss in this case, oh, I should beg your pardon, because this is Gauss, that is not SI units. Then you see that now this position here changes in frequency by some small amount, but that is sufficient to generate a phase change. And that simply means if we have a magnonic Bose-Einstein condensate, and if we locally heat the condensate, we move then here, we reduce the saturation magnetization, we locally change the phase. And therefore, we create a phase gradient, and therefore we should obtain a magnonic supercurrent. And that can be simply done by using the light of a laser. For instance, the light we use in the Brunner light scattering experiment. and that could create here a supercurrent. And indeed, if you look at the old data, we find deviations from the linear slope in this logarithmic representation. And these deviations indicate that we have an outflow of magnons. But let me show this to you in a somewhat more convincing way. And that is now simply an experiment where we use a specific heating laser, which is here, or here's the heating spot. And then we have the probing spot for the Brillouin light scattering. And then we can do all these measurements. For instance, we can measure the Brillouin light scattering intensity at the position where the heating spot and the probing spot coincide. So X is the separation between them. We can go 100 micrometer away from it, let's say here. Then we can go to 200 micrometers, we can go to 300 micrometers, to 400 micrometers. And in this way, we can measure the profile. And you see this data as a function of time, that this all looks, a lot of things happen, but of course, this data is somewhat hard to understand. But if I now let run the measurements, yeah, you see what happens. Yeah? That is with no heating pulse, so we only generate the Bose-Einstein condensate, which exists here over the entire region. And of course, eventually it decays, like we know, because of the residual coupling to the phonons. But if you have the heating spot, you see here that at the heating spot, the magnons disappear very quickly. Yeah? And instead, these two humps are formed here. Or in other words, the magnons are pushed out of this region. That is a little bit as if you would go to the marketplace of, I don't know where, let's say Vienna or Paris or whatsoever, and you have the marketplace equally filled with people, and now you go into the center of the marketplace, and then you cry, I have corona, I have corona. Then all the people try to separate from you, and you see this kind of bumps are immediately formed. These are shock waves, if you like to term them like that. Yeah. The people don't want to meet you. They are just moving out as fast as they can. And in this way, these humps here are formed. So this works. And the question is, what is it?
Sorry, Mr. Professor, we are running quite low on the time. So
yes,
if you can a little bit speed up.
Yes, I will speed up. I'm quickly done. Yeah, no problem.
Okay, thanks.
Yeah. And this is actually the scenario which you know from second sound in ultra cold helium. And what one has to do now, I have not shown much theory, and I will only show this equation. You have to solve the Gross-Bitaevsky equation, and you will end up with a condition which looks like a sound velocity equation, and I skip the details here. Yeah, because you get a sound velocity by which these humps now move away from you. And that is the parameters which enter here is only the dispersion coefficient, which you get from the dispersion, the nonlinearity, because we are in the nonlinear regime, and of course the number of particles. A very simple formula, and that is second sound. So we have magnonic second sound. It's called Bogoliubov waves, the second sound. And that is, of course, interesting because now we can have transport phenomena inside the Bose-Einstein condensate. And I find this very, very interesting because the Bose-Einstein condensate can be considered as a new state of matter. And then we have even excitations of that, such as the second sound. I skipped that here because that is not so important. So we discussed so far parametric pumping, Magnum BEC by spatial injection. I will skip the next part because we can also do it with temporal stuff. And I will come to my conclusion. As a conclusion, I would like to make you thinking. I don't have a questionnaire, but instead of the questionnaire, I think we can maybe just discuss a little bit. And here is just one idea. Everybody talks about quantum computing. Can we have magnonic quantum computing? What do we need? First of all, and this would be the very first step, we need to have something like a magnonic qubit. Can we have magnonic qubits? And this is my outlook. And my outlook is the answer, yes. And I show you with all what you have learned now today, how we can make a magnonic qubit. Just remember the right part here. That is just the dispersion of the backward volume mode. Here is the surface mode. Here in between, very, very schematically shown the Magnonic gas. You have learned we can plot it for positive wave vectors. We also can plot it for negative wave vectors. So we get it mirrored here at zero frequency, at zero wave vector. Pumping, we pump, of course, in both regions. So we form two condensates, one at positive and one at negative wave vectors. And these are wave functions. These are single wave functions, not a superposition of wave functions. And we can, of course, superimpose these two wave functions. And that is a qubit. Yeah, and you might remember the definition of a qubit. A qubit is just a coherent superposition of two states. People like to plot it on the so-called Bloch sphere. So that is a sphere. The surface of the sphere contains all possible superpositions of these wave functions if they are normalized to unity in amplitude. And so if we have only this BC, we can define it as a north pole. If we have only this BC, we can find it as the south pole. If we have a coherent superposition, we get all the states on the equator, and the position on the equator is defined by the relative phase between these two BCs. And what I'm not going to show you, because we can leave it to the question and answer section, we find methods how to prepare each state here on the surface of the sphere. And in this way, we are able to prepare any kind of qubit state which you like to have. And of course, we also can connect two qubits or more. And in this way, we can do qubit computation. I need to remind you, used a lot of quantum mechanical terminology, but this is at the very end still classical physics, but we can have something like a classical qubit. But if you look around into available algorithms and so on, there's much around where it is very favorable to do computation with these kinds of classical qubits. And in this way, you can get a big advantage developing this kind of technology. It's not yet a technology, it's the very beginning. And if you're excited about this, if you get excited about this, this might be a way to go. So with this, I would like to stop and thank you very much for your attention.
So thank you, Mr. Professor, for the very nice talk. And then there are questions from the audience. It should disappear. A little bit of a moment. Okay. So the first question: how do Bose-Einstein condensation generation depending on the yttrium iron garnet size? There is another part. Let's say by increasing thickness or using yttrium iron garnet particle.
Yes, you can change the thickness, and of course, one wants to have an optimum dispersion that is typically around 4, 5, 6 a micrometer. But you can also work with other thicknesses if you wish. So what happens is simply the dispersion is changed. I didn't really point it out, and I don't want to go back. If you plot the dispersion, usually it is plotted as a product of the wave vector and film thickness. So if you make the film thickness smaller, then everything is moved to larger wave vectors, where exchange becomes more dominant, and vice versa. So you basically, by the thickness, you can vary the amount of exchange energy to dipole-dipole energy. And what I showed you was somewhat optimized. I did not show you the last part. We also have nice data how we can thermally excite Bose-Einstein condensates. There we use different thicknesses and smaller structures, but it also works there. I can't hear you.
Sorry. So
Okay.
there is another question from Gia. To generate the Magnum Bose-Einstein condensate, what is a specific reason to use parametric pumping? Could I also generate the Bose-Einstein condensate by a normal RF, then by Magnum scattering? It can also approach to the Bose-Einstein state. Thanks a lot.
Yes, in principle you can. There are other ways, yes. The point is, what you usually do, you take a photon, a microwave photon, and you want to generate magnons. And the parametric process is very efficient because in all these processes, you have to meet energy and momentum conservation. Yeah. You can do direct excitation, indeed, that works, but this is always direct excitations at wave vector nearly zero. Yeah. And then you have to get the scattering process to the finite wave vector of the condensate. But it is possible. It is also possible by thermal excitation, something I couldn't show to you, but you can read the papers, that you simply well, basically the trick is that you fill it thermally, working at a finite temperature, and then cooling it down rapidly. Rapidly means on a time scale very fast to the relaxation time. And then the redistribution processes of the Magnum population, which have to take place, they can also lead to Bose-Einstein condensation. So there are many ways how you can do it. Another way, which also has been shown, because there is a nice connection to Piedro's talk, you can use spin torque to generate condensates. There are many ways. It's very universal.
Okay, thank you. There is another question from the Prague. So thanks for the great lecture. I wonder, are there any possible applications of the supermagnonic current you mentioned?
Yes, first of all, you can use the supermagnonic currents for information transport. Yeah, and of course, the idea is to take specific advantage of the coherency you have with a Bose-Einstein condensate. Yeah? I mean, if you would like to do qubit calculation or qubit computing, then you can only do it with these kind of objects, because a condensate is extended. You can use patterning to confine it. You can transport it. So we are thinking a lot about possible applications. A large other area I had no chance to talk about is external manipulation, for instance, via voltage, electric charges, and so on. That is all possible and gives you new degree of freedom. There are even new effects like the Aronoff-Kesher effect, which can be used for these purposes. So where at least predictions exist that these should exist.
Okay, thank you. There is another question. Thank you for the lecture. I have a question. How far are we from fabricating a functional energy efficient, comparable to CMOS, nanometer scale spin wave device? What do we need to fabricate such device? So there is two parts of this question.
Yeah, that is a different talk. I did not really go deeply into it. The questions which have to be solved is how to make nanometer YIG devices. This has been done, especially by André Chumak and by Philippe Perrault in my group, who leads a large subgroup just focusing on that. You need to efficiently generate Magnons and also efficiently detect the Magnons. The key point is simply that Magnons themselves have a very low energy. Yeah, and therefore these are objects. Magnons is micro electron volts compared to the electron volts you have in CMOS. Yeah, this gives you already the direction. The question is, how many Magnons do you need in order to get the process done? It's a very and there's another point: you can make devices much smaller for the simple reason that these are interference-based devices. Yeah. For instance, you need much less area to realize, for instance, a half adder, because you use interference instead of classic logic gates. So that all matters, and that can result in a very efficient logic one day. Don't forget that Magnons can have a very large wave vector. You have seen this today. Large wave vector means small wavelengths. Essentially, what we can do in Magnons is something where photonics didn't succeed. You can build photonic computers. Photonic computers have they are great, but they have two big disadvantages. Number one is the energy of the photon is too high compared to the Magnum. So magnonics can be more efficient. And second is the wavelengths of the photon is too large, because the device dimensions are defined by the wavelengths, and Magnons can be made down to nanometer wavelengths.